Well, g'day flatties and globe defenders, it's Critical Think from Down Under. In part 1, we were in the middle of discussing this particular slide from Exploring the Plains video, and we'll carry on from this point. I've still got a little bit more to say about this one. The other thing about this image on the right is that he's very conveniently moved that cranes down and says it's sinking, but you just can't do that, right? Sinking is a condition which happens because there's light bending up. Compression is a condition that happens when light bends down. So unless you can be going up and down at the same time, you cannot say that this is compression and sinking. And the other thing is, this is the position of the cranes on this day. This picture on the right was taken on the same day a few minutes after. So in that time, for me moving from a high location to a lower location, the cranes are not suddenly going to sink, right? That would be a function of refractive conditions on a particular day. But they're not going to suddenly sink just because I go to a lower elevation. So that is completely invalid, completely ridiculous. So here's two things that are ridiculous in this. So using a perspective diagram for a vertical surface and saying that something can sink in the process of changing elevation. And we get this. Compression is an optical phenomena. Okay, I'll go with that. Light is not actually bending. No. For you to get compression, the light must bend. That's it. It's a law of nature. That's how light works. And flat earthers are supposed to understand optics. A flat earther could never have invented this, because a flat earther doesn't understand optics.
Fuck off, you prick.
What a...
You
what an arrogant...
absolute prick. We understand optics very well, thank you very much.
How does compression happen without light actually bending? I don't know. No flat earther can actually show that. They just say, oh, it's because of a change in the angle or something. It's because the viewing angle gets tighter. Ah yes, there would be certain things that I would describe as tighter, but viewing angle wouldn't be one of those. So let's have a look at compression and light bending. Now another flat earther, Brandon Toy, did the fish tank experiment, and there's compression. The bottom looms up and is compressed. The top is not compressed, just like my ship. That's what compression does. Here's my fish tank test, my second one. There's the uncompressed, there's no density gradient, and there's the density gradient. The top doesn't sink down, the bottom looms up. Very easy to see in that one. And here's my first fish tank test. And here's Brandon Toy's bending laser. So he has a density gradient in his tank with compression, and that causes the bottom to be loomed up and compressed, and his laser is bending. Yes indeed, it's light that's bending. And here's my bendy light demonstration. Oh no, that's not bendy light, is it? Now what can I say about this diagram? Right, it's deceptive. You can't represent perspective in a diagram like this. The diagram on the top shows lines visually parallel. The diagram on the bottom means nothing. There is a correct way to represent perspective, but this diagram on the bottom is deceiving and it's incorrect, so that things don't actually get closer. They appear to get closer together because of perspective. But again, this is completely irrelevant in this case with the ship, because the ship remains at a constant distance and the perspective shrinking affects all parts of the ship equally, not just the bottom. Another diagram that has no relevance to the ship. This again is perspective lines on a flat surface that retreats into the distance. If you can have a look at the wall at the far end there, there's no compression happening on that wall. It just looks small because it's far away, but there's no compression anywhere visible on the vertical surfaces. So that's irrelevant. Again, I have no idea what this diagram is supposed to represent. I have no idea what's trying to be conveyed here. There's no explanation with the diagram. It appears like, and I cannot verify this because there's nothing to go with it, that just because this angle between Q and R here is small, that that would seem to mean that something here gets smaller first. I don't know, but it's crazy and it doesn't mean what he thinks it means anyway. Compression, yes. Light bending, no. So how does compression actually happen then if it's not light bending? What's this magical mechanism? It seems to me it's something that you just made up that has to happen in order for the Earth to be flat. And I think there's nothing more to it. It seems like that this compression can only happen when two things are true. There is the bottom of something and you are looking at the bottom of something. But light bending, no, well, that's not true. Then there's this mumbo jumbo about vision, parallel lines and stuff. How you see things is really not really relevant. When we take a picture with a camera, first of all, we're not using our vision, but second of all, light travels very predictably, except when there's refraction involved. When there's a refraction involved, then sometimes things can get a little bit out of place. But in general, light travels in a fairly straight line. And when you take a picture with a camera, all the items and objects in the image have a mathematical relationship to each other. So you're missing the information that is the distance. And it is quite possible to analyze an image, and as if you can work out the distance to something, you can work out exactly what the size of something in the image is if you know a couple of things about the image. And this is the analysis that we do when we analyze pictures, pixel counting, etc. And I know flat earthers don't understand it and think it's not possible, but every picture has mathematical relationships that are well known, that are built into them. So in the translation from 3D space to 2D space, you end up with these relationships that are inherent in the picture, and you can calculate them. It has nothing to do with how you see or how you perceive. And so vision space, the talk about vision space, it's some kind of philosophical study of how you see things and really doesn't have a lot to do with analysing mathematically an image. And we know that parallel lines are going to appear to meet in an image. That's just perspective. And here there is something here that is totally wrong. Right? He says here that on a globe, parallel lines do meet. Well, no. Even on a globe, they don't meet. These lines of longitude here are not parallel. Nobody said they were parallel. The lines of parallel are the lines of latitude. But the lines of longitude are never parallel. They're not meant to be. So you can't start a statement that is completely false and then make a conclusion from that. So this is nonsensical. Completely nonsensical. So that's it. So to summarise, there was an assertion that this compression here was due to a change in viewing angle. I've shown that the change in viewing angle is minuscule, and they're considering the wrong viewing angle anyway. They're considering the angle between the surface and the observer, not the angles that the ship, which is vertical, might present to the observer. And there are several other factors at play here. But one of the most important things is that when you're looking at the ship from higher up, you see no such compression. If it was dependent on eye level and viewing angle, you would see that exact same compression in the middle of the ship here. But you don't see it, because it's a load of bollocks, that's why. Now this particular day there was high compression, so there was compression visible. And there was an attempt by both Gary Wybenga and Exploring the Plane to make something of the viewing angle, simply because I had changed from a high height to a low height. And this is the age-old problem, making assumptions and incorrectly attributing the cause without actually investigating with a proper experiment. So I've got a few more images here, a few more blink tests, and let's start with this one. This is not the same ship, but it's a very similar ship. But this is a different day when there's no or very little refraction. And let's do the blink test on this one. Now, this is the exact same thing, changing viewer height. And as you can see, in this case, there's no compression, which is a very, very clear demonstration that changing viewing height does not cause compression. It wasn't that hard, was it? Look at this. And I'll zoom in on that one a bit. Look at that. And then we'll clear as day. A very good visibility, no compression, no inferior mirage. Absolutely fantastic. Look at that. And if we go zoom back out again, you can see that the water does appear to rise up in relation to the crane and no compression. So how about that? It's gonna rip the crutch right out of your nightie, isn't it? Let's go to the next one. Ah, yeah, fantastic. Beautiful day, wonderful pictures, no compression, none whatsoever. So there, that blows that theory out of the water. And just another couple there. As you can see, this port is working. The positions of the cranes change. The water appears to rise up. No compression.